Okay, I think we should get started. So greetings to those of you in our studio audience here. Thanks for coming. And greetings to those that are listening at home. Welcome to today's physics colloquium at UC Berkeley. It's a pleasure for me to introduce Professor David Goldhaber-Gordon of Stanford University. But please hold off your Stanford hostility because David has very deep roots in our department. His great uncle, Gerson, was a member of our department for some 55 years, beginning in 1953. I should say a beloved member of our department. David is internationally known for his work on the properties of electrons in all things small and confined spaces and all things quantum mechanical, beginning with his beautiful discovery of the Condo effect in a single electron transistor. And I should say that such is David's reputation for knowledge.
Here's what I found.
Yes. Wow. Such is his reputation for his deep knowledge and integrity that he and Patrick Lee were the two representatives on the select panel of 4 people that were convened by the Technical University at Delft to investigate their researchers' claim to have discovered Majorana fermions. But he's not here to really talk about that and his role as a Majorana narco agent, unless, of course, we ask him about it. Instead, he will give a talk entitled, "Can a solid-state quantum simulator help us understand materials?" But I hope in his overview, he will include in his presentation the beautiful discovery by his group of an entirely unanticipated new quantum phase in moire-twisted bilayer graphene. So without further ado, I'll turn it over to Professor Goldhaber-Gordon.
So, thanks, Joe, for the very gracious introduction, and I will get my my talk up in just a moment. Just make sure that I'm sharing the right thing. Okay. That should do it. And let's I'm going to start by sharing the screen. Great. It's yes. Yes. So I think actually the lights are the way I want them. If people find that the screen is not sufficiently bright for you, then please let me know. But I think that enabling people to be awake is probably a good thing at this time of day. It's really great to be back here and to see so many faces of friends whom I can partially recognize. I'd like to make this interactive. This is a topic that is, on the one hand, old for me. It goes back to my PhD, but it's also new for me. This is the first time I'm giving a talk on this topic, and I'd like it to be something where we can share ideas. And so what I wanted to share with you today was thinking about what it means to build an experimental system that's supposed to be a realization of some simple theoretical model or idea, and what role can it play in our thinking about physics. And so I'm going to call this, at least in one version, I'm going to call it an analog quantum simulator, as distinct from a general purpose quantum computer that's built from a set of qubits that can be configured and operate with gates that resemble in some ways the gates of classical computers, this will be something that's built to try to be as close to realization as possible of some model of interest. So we'll step into this in stages, but just to tell you where we're going, by the end of this talk, I hope you'll have a sense of at least what I believe an analog quantum simulator is, and some of my thoughts on what it might be good for, and hopefully it will spark a dialogue on that. And I'm going to give you this in the context of an experiment that is on the boundary between what can be calculated today and what can't be calculated today. So let me start with something that's surely familiar to all of you, a particle in a box. And so I want to ask, why do you think, maybe someone in the audience here, and then I'll repeat what you say, why do you think we, when we're teaching quantum mechanics, we start with a particle in a box? So we've all played guitar, and so if you have a guitar string and then you hold it down somewhere, then you change its frequency. Is that the idea, Mike? Yes. So I think that's actually a really nice answer. I would also say another reason is because we can solve it pretty easily. And but when I first took quantum mechanics, I was pretty naive about this. And the other day, I was talking in undergrad through particle in a box calculations, and I was reminded that my fascination with the idea of quantum simulation, though I didn't call it by that name at that time, it actually originated in my senior year of college when I learned about quantum dots or artificial atoms, and I'll tell you something about that in a moment. They're nanoscale boxes that trap one or a few electrons. Here's an example from slightly after that time of how such a box can be. All right. I'm afraid that my pointer is not going to show up there, but nonetheless, I'm going to just use words to say what I'm pointing to. But the little flat section at the bottom of the pillar there is where the electrons are confined, and it can indeed be brought down to 0, 1, 2 electrons. When I learned about this, I was shocked to realize that I had been implicitly assuming that we could make a particle in a box, and that was why we were calculating a particle in a box, rather than it being, for example, an abstraction of a hydrogen atom that was simpler to calculate. And so I was shocked to realize that I had been sort of naive about that, but simultaneously thrilled to know that now, for the first time, actually it was possible to make a particle in a box where electrons were confined in all 3 directions in a controlled way. And I would say that set me on my path for my PhD. And so if we look at what does this particle in a box look like, one kind of measurement that can be done on this is to look at the energy that it takes to add each successive electron. And so I don't want to focus on the axes of this plot right now, but if you just look at the peaks and the spacing between peaks, you can see that there's a particularly big spacing in the case labeled 2, and then the case labeled 6, and the case labeled 12. And it turns out that's the shell structure for this artificial atom or quantum dot. It's in 2 dimensions. It's in a harmonic oscillator potential, roughly. So I swept some things under the rug. I said it was a particle in a box. It's really better described as a particle in a cylindrically symmetric harmonic oscillator potential. And then in the vertical direction, it's really nicely in a square box. But in any case, you get this nice pattern, and you can see that it really appears to be a realization of a simple model that we can write down. So, so let's talk a bit more about what experimental realizations of simplified models can do for us. And so I want to invite you to give what are your ideas about why should we consider building an experimental realization of some simple model that we can write down? And there's no one right answer. In fact, I think there are actually multiple things that occur to me and probably more to you. Why would you, whether in the quantum realm or otherwise, why would you create a simple experiment that tries to realize an experiment that tries to realize some simple model? Yes. You can use it to calibrate your instrument, and I'd bring it beyond just calibrating the instrument. Also calibrate your understanding. Make sure that you really have a sense of what this model is doing. Admittedly, we're now in a world where simulations can be extremely powerful and convenient, and so it may not be necessary sometimes to calibrate your understanding, but certainly for calibrating your instrument. Yep. You want to go to a place where you know what the answer should be. Yes. Yes, so indeed. So the idea is you start for where you have ground to stand on that you're confident about, and you can do the direct comparison to theory. And I think that that's going to be really important. Then you build to more complicated situations where you don't necessarily know the answer. And I think that's going to be some of where we're going to have to go if we want to make use of truly computationally powerful analog quantum simulators. But I don't fully know how to do it in the cases that I'm talking about, and so we'll see that. So let me give you some of my answers for what it can do for us. So one thing is the light. So certainly that's what I felt when I first saw this artificial atom that showed shell structure, sort of like a hydrogen atom, but different because it's in 2 dimensions and harmonic oscillator. It was pretty much pure delight. It's not that it really taught us that much, except that it could be done, but that's worth something. And for my aesthetics, at least, it's different to see that in an experiment compared to a simulation. So another thing that it could do for us is build intuition. And so I think that's connected to what both of you were raising, but just more broadly to say, this is how this model behaves. Again, that's something that today simulations might be able to take over, but especially as we get into more complicated realms, and also the aesthetics of it, I would say that experiments have something to offer. And I would say another thing it can do is a quantitative test of the theory. Again, that's connected to what you were talking about, that in some realm we can test that it behaves in a way that might be very counterintuitive. I really like situations where there's some simple prediction that to me is just counterintuitive. It doesn't, and we'll see an example of that, at least one example of that. And finally, computing power. In the end, maybe we could build something out of quantum objects that could do a good job of simulating a quantum aspect of the world, for example, materials, that we couldn't do with classical computers. And so to me, that's a tantalizing prospect, but it's also challenging because of deciding when we can trust that. All right, so before I go further, I'm contractually obligated to tell you something about the Condo effect, which is not the bulk of my work these days, but I haven't been able to fully escape it in the decades since grad school. So if you take a chunk of metal that has a small scattering of magnetic atoms in it, for example, a chunk of copper with a few iron atoms in it, a part per million of iron, then it shows very striking behavior at low temperatures that was seen in the 1930s. It took decades to understand that this was related to the spins of the iron, because when it was first seen, no one knew that there was iron in what was thought to be pure gold. So it took decades to understand that that there were in fact magnetic spins there, and then Jun Kondo was responsible for the key insight in how magnetic atoms could produce the effects that we're seeing. But I do want to take a moment to say that one of the key experimental sets of work that showed that magnetism was important here was by Miriam Sarachik, who we lost just this month, and who is a great experimentalist and a great ambassador for physics. So, so in any case, at high temperature, the spins on the iron atoms are free to point in any direction, but at low temperature, those spins get screened by electrons in the sea, the copper around them, and form a singlet and become inert. And it turns out that this has now been understood to be very much connected to the low energy physics of the Anderson model, and I'll talk about that going forward. So, so let me give an example of an experiment that to me would, so I told you that an experiment that gives the light, one example was this artificial atom experiment, an experiment that gives intuition. So the Condo effect was seen in a certain sense in the 1930s in terms of the experimental phenomena, was understood to some degree in the 1960s, was really understood better in the 1980s, and became a benchmark for lots of experimental and theoretical techniques. But I would say that when I entered grad school in 1994, probably the really deep understanding of Condo effect was restricted to a small number of theorists. And it was a bit more of a mystery for the larger group of people. And I won't go into the details of it, but I do think that building an artificial system, in this case, one of these quantum dots, where the quantum dot acted as the local impurity, if it had an odd number of electrons, as you see in the middle range down here, the middle of the color plot in the bottom is a situation where there's an odd number of electrons, then it acts like a magnetic site, and the electron can hop on and off the local site, as you see in the cartoon on the top. The electron can, an extra electron can hop on, for example, and then an electron can hop off, in total flipping the spin on the local site, and that's what ends up producing the screening in the system that forms the singlet. So I just want to focus on if you look at this picture, those of you who are used to looking at this, in some ways it's characteristic of so-called Coulomb blockade in these quantum dot-based systems, but a very unusual part of it is the bright white line that goes horizontally at 0 across this middle diamond. And that is showing that something about the electrons is reorganizing right at the Fermi level. And that's a manifestation of the screening cloud that forms. So I would say that this set of experiments really gave this and many other experiments done in this area, actually being able to make a tunable realization of this model, which previously had just been applied to, say, iron and gold or cobalt and gold, but instead a realization where we could determine the parameters and tune them, really gave some intuition for what was going on in the Condo effect, so that it could be democratized in a larger group of people who could think about it. So that's an example for intuition. I should also pause now and just say that if there's something that you want to ask a clarifying question and you're in this room, or if you're on Zoom, please don't hesitate to do that. I'll leave time at the end to answer questions that are sort of more exploratory, but if there's something that would fit best in the flow, don't hesitate to ask. I'm happy to be interrupted. It's better that way. Yes. 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 Sorry I was sort of sketching this and not explaining it in detail. The idea is that there's a potential well in the middle that can hold, in this cartoon, can hold up to 2 electrons. If we put 2 electrons in, there's a higher energy because the 2 repel each other. And that's what's supposed to be indicated by the higher line there, that putting a second electron in takes more energy. On the left and the right, there's a sea of electrons filled up to a certain energy. And so electrons can hop from that sea onto the local site and back off. And the vertical lines are intended to be barriers to that hopping. Does that make sense? And something else I should have said is, if you look at the picture on the top right, this is an electron micrograph of the structure that was used to confine electrons in a semiconductor. And I'm happy to talk to people in more detail about how that's done. But it's confined on sort of the 100 nanometer scale, the electrons. All right, so that's intuition. Now let's move on to quantitative testing. So let's start on the left, the bottom left side, and let me just start with saying that, well, let me start by saying that when this screening cloud forms, there's a new energy scale that comes into the system that is related to the bare energies of the electron interactions and the hopping, the things that we would use to describe this model of the system. But even though it's related to those numbers, it's related in a very unusual way. It's related it's exponentially sensitive to the bare quantities that come into this. And I'm not sure whether I made this large enough, but if you look at the TK, which is the Condo temperature, or that energy scale, you can see that there's a prefactor, and then there's e to some power, and this power is a ratio of different energy scales. And what I want to just say for now is that those energy scales are scales that we can separately measure in this system, and we can tune them. So unlike, say, for cobalts in gold, where we might have to sort of make a phenomenological assignment of the hopping rate or the coupling between a local spin and the reservoir. In here, these parameters, which are epsilon naught, which is the depth of an energy level below the Fermi level, and U, the charging energy, and gamma, the tunneling rate. These are all things that we can measure and we can tune. We can tune them electrically by just putting voltages on these tiny electrodes. So this is a rather counterintuitive behavior, this exponential sensitivity on the bare energies of the system. And it was predicted by Duncan Haldane back in the late 70s. And no one could test it because there wasn't any way to make epsilon 10% larger in cobalt. You could just replace the cobalt with iron, but you can't continuously tune it. Here we could continuously tune, and what you see on the bottom left graph is the measured Condo temperature that we extract as a function of, on the horizontal axis, basically the ratio of epsilon 0 and gamma. And what you see is it's on a semi-log scale. The vertical axis is exponential, the horizontal is linear. And so the fact that locally it's a straight line tells you that this is an exponential dependence. The fact that it's a parabola is because we can tune all the way from 0 to 2 electrons, but let's ignore that for the moment. Look at that slope of that line. All right, the fact that it has a linear slope there on a semi-log plot tells you it's an exponential dependence, as Haldane had predicted, and I was pretty pleased with that. But then I said, let's be greedy. Let's look at what is the slope of that line, because after all, it's in dimensionless units. And the answer was that the slope was 3.05. And it's supposed to be pi. So that was really pretty remarkable that it was so close to what it was supposed to be. And so I said, well, that means maybe we can take this model pretty seriously. And both the experimental system and the somewhat, I talked to Haldane about it. He certainly didn't expect that it would be this close for the exponent, and other theorists didn't either. And then I said, let's be greedier. Let's look at the prefactor of the entire thing, this energy scale that's the harmonic mean of two of the energies, tunneling rate and charging energy, sort of a bandwidth for the system. And surely that's not going to be right, but it was in fact within 10 or 20% right. And that shocked everyone, including me. And that set me off on saying, well, maybe we can take these experimental systems more, these model systems more seriously as quantitative counterparts to the model. And simultaneously, we're sort of stressing the experiment and the theoretical model. Maybe we can take that comparison more seriously than I had thought. So that's sort of an introduction to the idea of quantitative tests, because and this sort of came out from saying, well, I would have been satisfied with less, but actually the quantitative test seems to really match quite well. Another example in Condo effect of quantitative matches is, this is something rather counterintuitive. I guess the other one was also, but if you look at the peak that I showed, that bright white line, a cut through that is shown in the bottom right corner, showing a conductance at that peak that's on the order of E squared over H, which is the conductance of a perfect 1D wire. And the prediction was, for this geometry, if you're tunneling through the magnetic impurity, that the conductance should be 2E squared over H. That is twice the conductance of a 1D wire, or the conductance of a 1D wire that both electron spins can flow through without interfering with each other. And that's really quite a head scratcher for me, that we have a box of electrons and we know that we're only allowed to jump one electron at a time onto it. So when an electron goes on, it should block the other from going on. And yet, so you could argue that maybe like a Fabry-Perot cavity, that if we're shining light at something with low transmission for the two mirrors, if the mirrors are well matched, you should still get 100% transmission. But now if we have these two spins and the electrons repel each other, it's pretty counterintuitive to me that you should get both sets of electrons going through without messing with each other. And I'm being a little bit disingenuous in the sense that I do understand why it's supposed to be 2E squared over H, and we can talk about it later, but still it is a striking prediction. And Leo Kauenhoven's group demonstrated that, in fact, you can get pretty much to 2E squared over H in this sort of geometry. And so that was pretty exciting also, that you can get this counterintuitive higher than one conducting channel through a box. All right, so so we've gone through the light intuition building quantitative tests of theory, and I'm going to not go yet to the computing something that is actually computationally useful beyond classical computers, because I haven't yet shown you something that would justify that. But let's now go to thinking about how we understand materials. What are our theoretical and computational tools for it? And here I'm talking to an audience that in some cases knows a lot more than I do about this. So please accept my my oversimplification. So one type of tool that we have to understand materials is what's typically called first principles or ab initio calculation. where one's just taking the structure of a material, or maybe even calculating the structure based on some known interactions between atoms, and then calculating from that, for example, band structure for the material. There's an example given at the bottom left from Marvin Cohen and Steve Louie at Berkeley have been among the pioneers in this area, and Steve in particular continues to be at the cutting edge of this. And so you have an example of a band structure calculated for a particular material. And what this allows is some direct comparison, quantitative comparison between theory and experiment. The weakness of it is that you have to make some approximations to put in interactions. It's not clear what's and not just approximations, it's not usually clear what's a well-controlled approximation. So you have to do it a bit ad hoc, and maybe you find that a particular way works well and you stick with it. So again, please forgive my naivete and correct me in the later on. But I wouldn't say that this is a failure in any way. Physics is all about making approximations, and in fact, even in particle physics, the way that we understand the world is through effective field theories that are just some approximation to a field theory that applies in general. And so I wouldn't say that approximation is any failure, but still, here we have to make some compromise on the degree of control of the approximation. Another approach, which can be merged with the first one, but I'll sort of cast it as in contrast, is many body computations. And so there typically we'll start with an effective model, some simple Hamiltonian that we can write down. That's surely not right for the whole system, because dealing with trillions of electrons is just out of the question. So there's an approximation made, write down an effective Hamiltonian, then solve that model and either analytically or computationally describe how it should behave. And there, an advantage of it is that you can engage with correlated electron states, superconductors, magnets. Disadvantage is that maybe you're oversimplifying in writing down the effective model. And this is where I think building model experimental systems really has a place, because if you really want to understand how good are your computational techniques, and what do those predictions that you're getting, do they really match what the experimental system shows? In a sense, you're comparing apples with at least a different kind of apple when you're comparing to a conventional experimental system, because it's not really the right model for that system. So if we can build a realization of a model that's an interesting one to deal with theoretically, then we can make that computation that comparison much tighter. And so from this point of view, there are a number of different types of experimental systems that people propose for quantum simulators. I would say that much in the public consciousness or in the physics public consciousness is cold atom systems, where you can have arrays of atoms, sometimes on a lattice. And so these have the possibility of trying to compare to lattice Hamiltonians that are important in condensed matter physics. There are also possibilities that increasingly are popular in superconducting arrays of superconducting structures, because of all of the work that's gone into making qubits for quantum computers. I'm going to talk about a different one that's based on semiconductors mainly. So that doesn't mean that this is the best way to do it. I do think that it has some advantages. And so let me talk about these nanopatterned model systems in semiconductors. And specifically, I'm going to talk about some of the advantages that they have, and some of the disadvantages. And the disadvantages, I think we may be starting to overcome. So advantages include we can design a Hamiltonian. We can say, all right, we want this to be the Hamiltonian of the system, and not only can we build the system to realize it, but we can actually measure all of the quantities involved, all of the key parameters, and for most of them, we can actually tune them in situ. So let me just give you an example. Here is two quantum dots next to each other in the red and the blue, and I've written the Hamiltonian on the left side. And for those of you for whom it looks scary, really the first term is just electrons in the reservoirs in the top left, top right, bottom left, and bottom right. The next one is electrons on the, the first, yes. The next one is electrons on the two sites, on the two quantum dots. The next one is interactions between electrons if you doubly occupy one of the quantum dots. The final one in the parentheses is tunneling on and off the quantum dots into the reservoirs. So they're all really pretty simple terms. And then the last term that's not in the parentheses, the terms in the parentheses are just all doubled because we have two sites. And then we have the interaction between the two sites, that if you put an electron on one site, it makes it harder to put an electron on the other side. So pretty simple Hamiltonian. Now the next advantage is that we can measure and tune all the key parameters. So if we think about the system, I'm not going to go through all the details, but we can change two of the voltages that are labeled P1 and P2. These are named as plunger voltages because you can imagine that they're, as in a piston, they can be squeezing the electrons down or pulling out and allowing more electrons in. So we can change these two plunger voltages. And when we do, we change the number of electrons on each site. And so I've labeled N1 and N2, or N1 and N2 plus 1. We can add an electron to one site or to the other. And the reason that these lines do not cross each other is because when we put an electron just now on one site, it makes it harder to put an electron on the other site. That's why in the little circle, there's a space between these sets of lines. So there's the stability diagram for the system. Now let's look at the experiment. And here are the measured conductances through the system. And I think now might be a good time to do the opposite of what I was doing, right? To turn the lights down a little bit. And I hope that you can see that they bear quite a striking resemblance to the very simple cartoon version. And what that tells us is that we really know what are the tunneling rates, what is the charging energy on site, which is U, the charging energy between the two sites, U prime, the tunneling rates. So we know all of the parameters of the system. And as I said, most of them we can tune. So so this is from about 5 or 6 years ago. So because it took about 24 hours to take these data. So first of all, it was a particularly stable device. And secondly, we just wanted to make the point we really can nail this down. We don't typically do it in this excruciating detail. Is that clear? So the question was, could this be done 15 years ago? Let me think. There are a few reasons it might have been tricky. One is just the stability of the amount of charge noise. It's still not very well understood what causes charge noise in these systems, but people have been getting better at producing heterostructures and doing fabrication to lower that charge noise, and probably I could do even better if I talked with some of the spin qubit people who must be having to deal with that. So that's one issue. Another issue is just the electronics, getting that, this was done with digital to analog converters that have 20 bits so they can do part per million changes in voltage. Yeah, 15 years ago that was available, but it, maybe not quite 20 years ago. So there are a number of things that have to happen for this. Oh, also another thing that was developed, a bit more than 20 years ago, but didn't diffuse to the whole community at that point, was the idea that you have to, it's very easy for the electrons to get excited by signals coming from room temperature down the lines. Even just a resistor at room temperature, its black body radiation or Johnson noise is a blazing inferno going down into a dilution refrigerator. And let alone if you consider Wi-Fi. So maybe in a certain way, there was a time in the past when things were better, when we didn't have Wi-Fi everywhere, but we've now learned to do filtering on the lines, and that turns out to be quite important. Does that answer reasonably? All right, so now, so far I've shown you that we can design the Hamiltonian and measure and tune the key parameters, but what about quantitative comparisons of the experiment? First I'm going to give a hand-waving picture of this, just some of the areas where this has been applied, and then I'll dig into one example that I think is particularly rich. So people have made arrays of quantum dots of different kinds, and I'm showing 4 examples. In the top left, there's an example from just this last year that was that was showing exploring an old idea that was kind of a cute idea, but it's not clear that it applies in materials, called Nagaoka ferromagnetism. If you've ever played with one of those puzzles that has 5 by 5 squares, and one of those 25 squares is missing, and you need to move the squares around in order to reassemble a picture, then you know about Nagaoka ferromagnetism, or at least the first ingredient for it. Imagine that you have an array of sites, and each one is filled with an electron, except for one. There's one hole. And now you ask, the electrons are free to choose their spin. We really don't want to have 2 electrons on a site. What state will the electrons go into? So if you didn't have a hole, many of you may know that the state should be an antiferromagnet in most cases, because the electrons can spread out a little bit. If they have opposite spins from their neighbors, they can virtually hop to the neighboring site and come back. But if you put one hole in, then it's possible to get something exactly opposite. That is, if you have the same spin as your neighbors, then, sorry, I need to reconvince myself. So, yes. So if you had an antiferromagnetic background and this hole was trying to move through that background, it would need to keep flipping spins. And so what that would do is it would put increasing numbers of spins next to the wrong neighbor. Whereas if all of the spins were polarized in the same direction, the hole could freely move through the lattice. So I'm probably not doing full justice to that, but the point is, the Nagaoka ferromagnetism idea was, a bit of a toy idea. It was clear that putting one hole in a Mott insulator doesn't make it into a ferromagnet in practice, but in this example that's really built to be a realization of that model with 4 sites, 3 of them occupied, it turns out that you get ferromagnetic correlation there, that all the spins align. So another example is 2-channel Condo, where you have 2 reservoirs trying to screen the local spin. And that turns out to have a quantum phase transition where the 2 reservoirs compete to screen the spin. And that's something that my group studied. Another example that that's relevant to what I'll say later is a different sort of model system that is again a realization of Condo, but now where you can build an arbitrary number of channels. And this was work by Frederick Pierre and Saclay. And then finally, another example that's popular is studying the Hubbard model, specifically the Fermi-Hubbard model. This is an example of an array of 3 sites that interact with each other, and where they saw a metal insulator transition. And the top left and bottom right were done by Lieb and van der Zijpen's group in Delft. So these are just examples. I'm not showing you the quantitative comparison, but I would say the top right and bottom left, the ones that were from my group and Frederick Pierre's, we really did detailed quantitative comparison and really pushed the limits of cutting edge, in this case, numerical renormalization group calculations. So another thing that so I'll get more into quantitative, I'll actually show you quantitative comparison, but another possibility, another advantage of this sort of approach is that one can locally probe every site. How can you do it? Well, I showed you this picture where we had these 2 dots, blue and red, and they were only capacitively coupled to each other, so we could measure conductance through just one dot or just the other dot. So that allows us to probe them separately. Another example is in the top right. If you look above the 3 dots in a row, there's another one that acts as a sensor, capacitive sensor of the other dots. And so its conductance is affected by the occupation of the other dots. And so that's another way to locally probe each of the sites. All right, so I told you about advantages of these systems, but you've noticed that these are 1, 2, 3, 4 sites. These are not the 1,000 sites that cold atom people can get to. And that's for a reason. It's hard to scale to many sites because every one of these quantum dots, unlike every atom or every period of an optical lattice, is different. It has a slightly different shape. And so if we try to, even if we do all the tuning, which would be very laborious to try to make them all the same, they'd still have different ladders of energy levels. So it's very hard to see how we'd make all of them the same. We now, I think, have a way to really scale up and make them all the same in practice, but this has been, for most of the time I've been thinking about this, a limit. Another limit is that we may not be able to build every Hamiltonian we're interested in, and that's certainly a limit. It remains a limit, but it turns out that we've seen how to access a different class of Hamiltonians that I think is quite interesting. So let me now introduce our new system that we've been working on lately. And I put new in parentheses, in scare quotes, because it's actually in some ways a rather old system. Kostya Matveyev predicted decades ago that if you had a metallic grain, something that had a continuum of levels but a finite charging energy, so pushing an extra electron onto it would take energy. If you had such a metallic grain as opposed to a quantum dot with a discrete level spectrum, then that could act as a Condo system where the local spin would not be spin at all, but would be the occupancy of the local site, which would be n or n plus 1 electrons. N might be millions, but 2 different occupancy numbers would be the 2 states of the 2-level system. And then you'd be screened by a reservoir. There was a difficulty with this, which was that you needed to have this metallic grain coupled by one channel to its reservoir or reservoirs. And in fact, usually a metallic grain with an oxide tunnel barrier is coupled by millions of channels, each of them very weakly coupled. And so that's where things stood until Frederick Pierre figured out a way to break that impasse. So in order to build this kind of system, we need a large charging energy. So we have good dilution refrigerators. We can get down, if we need to, probably to 10 millikelvin electron temperature or a bit below, but we're not getting down to 1 millikelvin except by going to really serious international facilities for low temperature physics. So we need a large charging energy to start with. We have to have precise control of the tunnel coupling to that grain to the outside world. And as I mentioned, that's usually not possible in metals. We need a large density of states in this grain so that we have basically a continuum of levels so that every metal grain basically looks like every other metal grain. And as I've alluded to, you can't do all of these in either metals or semiconductors. You can get the this sort of threefold structure, that's a metal grain. That's the island in this system. And then on the bottom left, the top, and the bottom right, there are leads attached to it, but those leads are semiconductors. So this metal island is an ohmic contact, an intimately electrically connected contact to a semiconductor, to a gallium arsenide 2D electron system of the type that was used to study fractional quantum Hall effect going back decades. And in fact, fractional quantum Hall or quantum Hall is apropos because this is put into the quantum Hall regime where every one of the leads has one 1D mode that's coming in along one edge, and then one 1D mode coming out on the other edge. So how do we control the coupling of this mode to the island? Well, first of all, we better be sure that that coupling can be really good. That is, if we don't do anything to block it, that mode should go in with essentially no reflection. In fact, we've gotten to 99.9% transmission of the mode. But then we can reduce it from that with a gate electrode that's used to pinch this off and eventually reflect the mode. That's called a quantum point contact. And it turns out in the quantum Hall regime, that can be done very smoothly. And I don't take the credit for coming up with any of those insights. It was Frederick Pierre who saw that he could put together these ingredients, and he used it for really beautiful things, including the picture that I show here is looking at renormalization flows for 3-channel Condo and showing the different fixed points for the system, and just an amazing comparison between what might be expected. I've never seen an experimental picture of renormalization flows of this sort, even though they're at the core of thinking about quantum criticality. So the point sort of partway up on the right is an intermediate coupling fixed point that's a quantum critical point in this system. All right, so I saw this and I said, well, what if we took this and we made 2 of them? And that's what we did. And the picture up on the right is the picture of those 2. Why did we want to do that? Well, besides, if one is good, 2 must be better. There was actually a good reason for this. If you want to understand magnetic impurities coupled to each other, then which is important, for example, in understanding heavy fermion materials, a set of materials where you have an array of magnetic sites, and they're believed to be relevant to the strange transport behavior. If you want to understand that, a nice place to start would be going from one magnetic site to 2 and coupling them. And we had tried doing that in quantum dots, and we had realized time and again that it was not possible to do that coupling without destroying the quantum critical behavior that we were looking for. But here it seemed like it might be possible because of the different realization of Condo effect. And so we set out to build what's known as the 2 impurity Condo system, two spins coupled to reservoirs and coupled to each other. It turns out when we talked to a theorist, Andrew Mitchell, about this, he pointed out, no, that wasn't the Hamiltonian we were building. We were building something that no one had written down before, where the coupling between the 2 sites was actually also a Condo type coupling. It was not a simple antiferromagnetic JS1.S2 coupling. And I don't have time to go into the distinction or why that would happen. But it turns out this is a system that, on the one hand, it's disappointing. I had wanted for so long to make a 2 impurity Condo system, but on the other hand, it's pretty exciting that it's building a realization of a new system that actually may give better insight into the heavy fermions than two impurity Condo would. So we have these two sites, each of which has two states, two different charge states. And when we tunnel from one site to the other, we change the charge state of both of them. So we can look at charge stability diagrams, kind of like what I showed you before, and we can get a handle of all the parameters in the system. And the tau c that I show on the left, that's the probability of transmitting by tunneling through from one dot to the other. And then these pictures were tuning the occupancy of both dots. And so you can see that there's quite a good match, for example, bottom left to bottom middle between theory and experiment. But I like to say, some of you have probably heard me say this before, that that color maps are beautiful, but they hide a multitude of sins. So let's do line cuts through this so we can actually look at what they look like. On the left is the experimental results. On the right is numerical renormalization group calculations by Andrew Mitchell. And you can see that they don't look absolutely the same, but they look awfully similar. Also, at least for now, we've had to weaken one of the things that I wanted to do, which is to say, we measure all the parameters independently and then just plug them in and say, computational theorists, please plug them into your model and don't share information with us, just let's compare blindly. Here you can see that what we know in our experiment is tau, the tunneling probability, and what goes into the model is J, a sort of effective spin coupling. And I hope to really nail that down so that we don't have that loophole anymore. But you can see that those look similar. I see that I'm near the end of the time, so let me say one more thing here, and then I'll come to the sort of denouement. As we change the relative coupling between the two local sites on the one hand, and of each site to the outside world, that's tau c, the coupling between the two sites, is on the horizontal axis, and tau, the coupling to the outside world, is different for each curve. What you see that there's actually a maximum of conductance through the two sites when the two couplings are close to matched. If either of the couplings is too big relative to the other, then you form a Condo state just with the reservoirs or just between the two sites, and no conductance can occur. So it turns out that theoretically there's a prediction for a universal conductance curve as you change the ratios of these parameters. And what I want to focus on is that there should be a quantum critical point at a particular place in this space. And that is, for example, if we look at the peak in conductance, the case where there are three degenerate charge states, and we detune from there, there should be a universal behavior of the conductance as we do that detuning. And indeed, you see on the right-hand side that if we plot a particular extracted parameter, this T star on the horizontal axis and conductance on the vertical axis, all the data collapse. That's for just detuning, staying at the constant temperature, but detuning the couplings from their critical values. If, on the other hand, we change temperature, then you can see that we have conductance versus this T star at different temperatures. If we plot against T star over T, our actual physical temperature, you can see that again, the curves all collapse onto each other. And so, and in fact, this collapse and the power laws that occur there are highly non-trivial. They're different from other models that we might use. And so we've been able to identify a new quantum critical point in this system. And we've been able to do it by detailed comparison to numerical renormalization group calculations that are really cutting edge. I mean, cutting edge in terms of the programming, cutting edge in terms of using a supercomputer, to the point where Andrew said, if we added one more lead to the system, he couldn't do the calculation anymore in a realistic time. And so that, I think that that's I want to say, well, it's one of the two messages I want to leave you with, that we're really up against the boundaries where we can test rather non-trivial theoretical predictions. And it's really quite exciting the degree to which we can build a realization of those and make those tests. On the one hand, that's great. On the other hand, it means as we go forward, it's exciting that we'll be able to go beyond what the sort of gold standard low energy calculations can do. But on the other hand, we're on our own. And so I'd really invite you to come on a voyage with me and explore, what are the kinds of interactions between theory and experiment that can occur when we build model systems that are simple and elegant, but go one step beyond what anyone can calculate with NRG, let's say. So that's one message I want to leave you with. And the other message I want to leave you with is that this system that we built, it wasn't the Hamiltonian we intended, but it actually is a Hamiltonian that looks like it might offer insight into the so-called coherence of a spin lattice in the heavy fermion systems in a way that the two impurity Condo Hamiltonian couldn't have done. And so I think that's sometimes unexpected aspects can, even when we're trying to design things, can be really exciting. And I guess I said two things. I'm going to say one more thing, which is I said that scaling this would be hard, but now because the islands that we're building this out of are metallic islands, as long as we can make them almost exactly the same size, it doesn't matter that each one will have some random eigenstates for electrons because they have a continuum of states. So our lithography is good enough that we can basically make every metal island identical to the extent that it needs to be. We can tune the energy levels to be the same on every island. We can measure that. We can tune the tunnel couplings to be the same. And so it should be possible to make not only 2, 3, 4 sites, but actually a 1D chain, a 2-leg ladder. And I think even if we really stretch a 2D array, and a 2D array of what? It's not quite a Hubbard model. It's not quite the standard Condo lattice, but I think that it's something that'll be exciting to explore, and I'd be interested in what people think of that. So just to acknowledge the people who did this, the leaders of this experiment were Winston Paus and Lucas Peters, a current and former student in my group. Andrew Mitchell did the remarkable calculations. Mark Kastner, my former advisor, jokes that he's now come back to work as a postdoc in my group, but he's been a wonderful influence on us. But postdocs in my group generally actually turn knobs in the lab, and I think we all agree that that's probably best to leave it as it is, that we discuss physics rather than have the professors come and break things. Ulf Genzer and Antonella Cavana grew the heterostructure. Mike asked, could this be done before? Part of what's key is charge stability, and that was really important. And Andrew Keller took some of the data and did some of the samples and measurements that I showed earlier in the talk. And this was all supported by DOE through Stanford Institute for Materials and Energy Sciences. So with that, let me turn the lights back up. And I know I ran sort of to the end of the time, but I am happy to stay around and answer questions either by Zoom or in person. Yes. Yes, so the question was on how do we read out, and are there things that we can read out easily and other things not so easily? And as you alluded to, the cold atom systems are really particularly good at getting, say, full counting statistics, knowing where every object is in a lattice, and what state. These systems are particularly good for full control of every local site, though the cold atom systems may be catching up. They're also good for getting to really low temperature. So I think what we're really good at measuring is local density, tunneling density of states. So that's what numerical renormalization group naturally gives us. And I think that there are noise measurements that can be made. So yeah, maybe it's something to explore more, but mostly these will be either some compressibility measurements through capacitance or a local density of states measurement. Hi, James. So the question is, are these devices always reproducible? And in general, in quantum dot type devices, the answer is no. There, there might be one junction that is particularly noisy when we sweep the gate. This has gotten better with, learning to do the fab better and with the right heterostructures. But certainly it's a consideration, and there are groups like Lieven van der Sijpen's group that I mentioned a couple of works from that have started to do automated tuning of their structures. So yes, it's a challenge, but it's not sort of, every device has one bad thing. Is there, yes, a question on Zoom. So from the Zoom, we have from Krzysztof Pomorski. The scalable electrostatic qubits implemented in CMOS have the chance of implementation of quantum computation at large scale, or do you suggest other technology? So, so let me unpack this. This statement, scalable electrostatic qubits, I think that he's referring to what I would call spin qubits, but electrostatically controlled, electrons trapped in local sites. Will that scale? I think that it's not obvious still what's going to win. I think that there are advantages in the ion systems, advantages in the different solid state systems, superconducting and spin-based, advantages in some of the optical approaches. And yeah, maybe it's a longer conversation, what are they, but I do not feel I know enough to say, yes, one of them is the one to back right now. And I would not be shy of saying if I believe that I knew. Yes, Joe. Great. So good question. So Joe, I probably should have taken the time to explain the sort of strange nature of these quantum critical points compared to what people are normally used to. This is a quantum, how can you have a quantum critical situation or a phase in a situation that you have only one or two spins or two level systems? And the answer is that the thermodynamic limit comes from the reservoirs. So those are large. And so the different phases are, for example, a phase, in this case, it's a phase where the local spins, they're not real spins, they're these pseudo spins, these two charge states, are screened each by its own reservoir. That's one phase. Another phase is where the two form a singlet together. That is, you have one extra electron, but it's split between the two sites. So either you have the extra one on the right or the extra one on the left. And that's the type of singlet that's formed. It's a sort of icing-like singlet, or icing, sorry, ice 0SZ. So those are the two phases, and right in between, you fluctuate between them, and that's how you can get transport through the system. Great. Well, thank you very much for welcoming me here. It's great to do this in person, and I hope to talk with a bunch of you either now or later.